In this video we're going to look at quadratic sequences which are related to quadratic functions. So let's just start, I think, with a sequence, the sort of thing that we might get in an exam question. So we might get something like this: 6, 17, 34 and 57, and it might be represented like this as a continuous sequence that would go on and on. So the question is, what is the function that generated this sequence, which we call very often the term-to-term rule? So what is the function of n that gets us from 6 to 17 to 34 to 57? Well, the first thing you want to do is have a look at whether this is indeed a quadratic sequence, and that's done by looking at the differences between the numbers. So in this case what we've got is a difference of 11 between 17 and 6. Subtract 17 from 34 and you get 17. And between 57 and 34 we've got a difference of 23. Okay, that's called the first difference, and we'll call that for short d sub 1. So just like with a linear sequence, we've got our first difference, but our first difference, unlike a linear sequence, isn't constant. So it's changing, it's increasing in fact in this case. So our second difference should be constant with a quadratic sequence. All right? So 17 minus 11 gives us a second difference of 6, so we'll call that d sub 2. And 23 minus 17 gives us a second difference of 6. And presumably if we continued the sequence, we would continue to get a second difference of 6. Now, all very interesting, but how does that help us find the term-to-term rule? Well, for that, it's a good idea if we have a look at what we're dealing with here. If I use a graphing calculator, which I've done just before making this video, to take the function that produced this sequence and put it into that calculator, what can we see? Well, we get something like this. What we've got here, there we go. What we've got is on the x-axis, which in fact with a sequence wouldn't be called x, it would be an n-axis. Let's just make it clear that I've erased that. Okay. So this is the number of terms. In other words, this is the fourth term. Here would be the first term, then the second term and the third term. And the value, which we call, sometimes people call this the t-axis or t for term. I prefer u. T for term seems a bit strange, but u, which is also a very common notation. So u is the value of each of these terms. And for the first term, of course, we know that the value is 6, so that would be on our parabolic curve here, and over here this would be 6. The second term we read off on the u-axis 17 here, and the third term we know is 34, so that would be about there. And the fourth term we wouldn't be able to fit on here, so it would just be just off the edge here. But you can see what's going on. We've got a quadratic sequence. We've got a pattern of dots that are built on this curve here. And what we're going to do next is find where that curve intersects with the u-axis, okay, which would be here. Because, as we've seen in previous videos, that will give us our constant in the function, okay, the intercept with the u-axis. Alright, so that's interesting, but let's go ahead and see if we can work out, find the solution to the problem. So let's just erase all these marks here. Now I am going to graph this so that you can see what's going on. Usually you wouldn't need to graph it, but I think initially it's a good way of seeing how this works. Okay, so let's draw some axes then, about here. And we'll keep it nice and straightforward. So we'll just have 1 here. So 1, that's our first term. So we'll call that axis n. First term, second term, third term, fourth term, fifth, sixth, seventh, and eighth. Now we haven't got a fifth, sixth, seventh, and eighth term, but it may well be that we get a question which asks us to find higher terms called finding the nth term. Okay, so we'll just put those on our graph in case we need to go up to the eighth term. And on the u-axis, we're calling it 2, 3, 4. We'll number it like this. So 50 and 100. And if we need it, we can go right up to 150 by the looks of it. But that'll do for the moment. Okay, so plotting our values on here. Let's use a different kind of pen. Okay, let's have green. So our first value is 6, so that would be about here. Our second value is 17, so that's going to be about there. Our third value, 34. We'll put that there. Fourth value, 57. And as I say, we wouldn't normally need to do this, but it just helps, I think, to illustrate what's going on. Okay, now the way of working here is to find what we call the zero term, as I say, which is where it intercepts with the u-axis. So I'm going to estimate that that's going to be about, well, it's about 4, isn't it? But let's find out what it actually is. Okay, so I'm going to make a little green box here, I think, so you can see that this, of course, there isn't a zero term, but we're going to use the idea of a zero term to find the, there we go, to find the term-to-term rule. So what I'm going to do now is just erase these little marks and extend this pattern back to find the zero term that we think is about 4. Okay, so let's go back to our blue pen here. Now let's stick to the brown pen, because that will just indicate that this isn't in fact one of our terms. Okay, so we know that between this and the first difference we must have a constant of 6. Okay, and if we subtract 6 from 11, we're going to get our first difference, zero term if you like, the difference between the zero term and the first term, in fact, which is going to be 11 minus 6, 5. Now, it's quite easy to get our zero term if we just think a little bit. Here's our first term, so it goes 5, 11, 17, 23. That must mean if we subtract that 5 from 6, then we're going to get a first term of 1. Okay, and just if you're not sure how that works, just check back. Okay, does this all add up? So we've got 1, 6, 17, 34, 57 now, and in that case, yeah, we've got a difference between the zero term and the 1 term of 5, and the difference between this is 11, and it all adds up to a second difference of 6. So good, that's done our little check. Our estimate was wrong. In fact, it was down here, wasn't it? But having a look at the graph, that does look about right, doesn't it? So we wouldn't mark a dot here. I can put some dotted lines here, nothing wrong with that. Just working lines. But we can see where it crosses now the u-axis at u equals 1. Okay, so the zero term is 1. Alright, now let's press ahead and solve this problem. So what we've been asked is to find the term-to-term rule that generates this sequence. In other words, we've been asked to find the function of n that describes this curve. So the way of doing this is quite straightforward. First of all, the u-intercept must give us c. So c must equal 1. So that's the first thing. So the 0 term gives us c. The next thing is this term here, in other words, the difference between the first term and the 0 term, gives us a plus b. A plus b equals 5. Now the a plus b and c, just in case you aren't sure what I'm talking about here, come from the standard form for a quadratic function. A quadratic function will always look like this. So the general term, if you like, is u, whatever the value is, so we'll call it n, will give us a, n squared, so any number times n squared, plus b times the n term plus our constant at the end, c. So we should bear in mind this standard form for the quadratic equation so that we understand what we mean by a, b and c. So a is the coefficient of n squared, b is the coefficient of the n term, and c is the constant at the end. Okay. Now, what we still can't do is work out what b and a are, because we know that a plus b equals 5, but there's a nice little trick here, which is to look at the second difference. The second difference is 6, okay? It's always 6, so it's 6, 6, 6. So this is the second difference. Let's just write that in here. And the rule for the second difference is that it is always, with any function, and in part 2 I'll do a little proof of this, but it's always 2a. So 2a must equal 6. Now if 2a equals 6, we can then divide both sides by 2 to get a equals 3. And if a equals 3, using this equation here, we can then say 3 plus b must equal 5. Therefore, b equals, subtract 3 from both sides, 5 minus 3, okay, is 2. So a little bit of simple algebra is necessary to get us our a, b and c values, but as soon as we've got our a, b and c values, it's all good news. We must be able to, we can reconstruct, if you like, what the term-to-term rule must have been that generated this sequence. So the trick is to find the 0 term, the first difference, the second difference, and then the 0 term, and that will give us a, b and c. Okay, now what I'll do is just highlight here our a, b and c so we can see it clearly. So there's our a equals 3, our b equals 2, and our c is the u-intercept, c equals 1. Alright, so our term-to-term rule, let's write that here, term-to-term rule is, okay, well, if a is 3, then 3n squared, b is 2, so plus 2n, and c is 1. So that's our term-to-term rule. And we can just check that that's in fact correct. Okay, let's just do a quick check here. So if we just check that we've got everything correct here, so we'll just write check here, by substituting in n equals 1. I think we'll do just 2 terms, but what we're looking for, we're trying to get 6. If we've got this correct, then this should produce 6. So 1 squared times 3 will give us 3, plus 2 times 1, 2, that's 5, plus 1 gives us 6. So u1 does equal the first term of 6, so it works for that. We can try one more. u2, well, u2 is when we substitute 2 into our term-to-term rule, so 2 squared times 3 will give us 12, 12 plus 2 times 2 is 4, gives us 16, plus 1, 17. So we know that the term-to-term rule is functioning correctly, and that's enough to tell us that our term-to-term rule is correct. Okay, good. Now, that might be all that you're asked to do, but many questions will either give you the term-to-term rule, or if you don't have the term-to-term rule, you derive it, it will then ask you what is the nth term. So, for example, it might say, what is the 8th term here? Or, shall we say the 7th term? So what is the 7th term in the sequence? Something like that. Okay, so if we're looking for the 7th term in the sequence, let's go back to our graph here. What we might want to do is just estimate this to start with. So there's our curve curving up nicely. And where's it going to be? Let's say it's about here. Okay. So in other words, our estimate, let's just write it up here. We're going to estimate that U7 is approximately equal to, so it's not accurate, it's just an estimate, approximately equal to 150. Okay, and all we've got to do to answer this question and find out what it actually is use our term-to-term rule. So, what is the 7th term in the sequence? U7, okay, U sub 7 if you like, is, so n equals 7, so 7 squared is 49, so 3 times 49, let's put that in brackets, 3 times 49. Now we substitute 7 into this part of the function, so 2 times n is 2 times 7, which is 14, so plus 14, and then the constant plus 1. Okay, well, 3 times 49 is like 3 times 50, subtract 1, so that will be 150 subtract 3, so it's 147, plus 15 gives us 157, 162. Okay, so that would be the answer. Just as a check, are we anywhere near 162? Well, we weren't far off 150, so I think 162 sounds right, and so I'm going to say that's correct. Okay, should we do one more? So we'll call this A. Let's try something like this. So here's the sequence that we're given: 14, 40, let's say, 72, and this time 110. 110. Okay, so slightly larger numbers, but everything should work out just the same. So let's plot this on our graph just to see what we've got. So we've got 14, that's going to be about here. Second term is 40, so that's going to be about here. Third term 72, so about here. And fourth term 110, so that's going to be there. So say we wanted to find the fifth term, I'd estimate again that that's about 150, that's going to be about there. Okay. Let's just, though, this time work on the term-to-term rule. What's the term-to-term rule then that generated this sequence, which looks a bit linear there, but it isn't going to be? We're going to find out what the u-intercept is. In other words, we're going to find the 0 term first. Okay. So let's work with a brown pen actually, so you can see clearly what's going on. So first difference, D1, is 40 minus 14, that's going to be 26. 72 minus 40, that's going to be 32. And 110 minus 72, well, that's going to be 38. And so my second difference is going to be 38 minus 32, 6. 32 minus 26, 6. So we've got our constant. That seems to be working out nicely. So we know that our second difference has to be 6. Now to find our zero term, well, if we just work backwards with this 6, then we're going to have 20 in the first difference, and 20 subtract 14 is going to give us our first term of, well, 14 subtract 20 minus 6. Okay? So if we plot it on our graph, it's going to be about here, minus 6. So you can see what's happening. This sweep is going down here, and it's going to turn, I'm guessing, around there. Okay? And then it proceeds up like that. Alright, now we do a little bit of algebra. This is the fun bit. So we need our A terms, our B terms, our C terms. Well, the C we can do straight away. So C equals minus 6. Our A plus B is this term here. In other words, 20. And our common difference is 2A, which equals 6. So if 2A equals 6, we've got exactly the same as we had before, actually. So A must equal, so let's write it in here, therefore A equals 6 divided by 2, in other words 3. So there's our A term there. Now if we substitute back here into this equation here, we have 3 plus B equals 20. Therefore B equals 20 minus 3, and that's 17. And that's all we need to do. I'll just highlight those quickly, because I think it helps. But we've got our A term here, our B term here, and our C term here, which is a negative. And that means our term-to-term rule, okay, our term-to-term rule must be, let's write it here because we haven't got much room. So our term-to-term rule must be, here's our A term, so 3n squared. Our coefficient of n has got to be 17, so B equals 17. And our constant, negative 6, so minus 6. So we're done. We've demonstrated how to get the term-to-term rule, but finally we must remember always to check. So it's very easy to make a mistake. Have we made a mistake? Well, 3 times 1, so this is U1. 3 times 1 is 3 times 3, so we've got 3. 17 times 1, 17. Subtract 6, so 20 subtract 6 gives us our first term value of 14. And 14 was exactly what we had as our first term. So it's worked out so far. Just a final check though on U2. Let's write that there. So U2 is going to be 2 squared, which is 4. 3 times 4, 12. Plus 2 times 17, 17 times 2, 34. Minus 6. Well, 12 plus 34 is 46. Minus 6 gives us 40, which again is coincides, is basically our second term there. And so having done the first and second term, that's enough of a check to be confident that we've got our term-to-term rule. Okay. But why do we have these kind of rules? How does the algebra actually work? Well, to explain that, it's pretty straightforward. We need to go back to our standard function. So our standard function for a quadratic is an squared plus bn plus c. And that gives us things like the second differences of quadratic sequences are constant and equals 2a. I'm going to show you how that works. You don't need to know because the rules that it generates are very straightforward to remember, but it's just nice to know where these ideas come from rather than using them automatically. Okay, so what we're going to do is use the standard function to generate general terms, so algebraic terms, for each of the terms. So in other words, if we've got u1, our first term, what's u1 going to equal? Well, it's simply when n equals 1 is substituted into this standard function, and then we get our value for u1. We get our first term. So in other words, when n equals 1, n squared is 1, so we get a times 1, which is simply a. Okay? When n equals 1, our second term, our n term here is going to be b times 1. In other words, simply b, so plus b. And our constant, of course, so we don't have to substitute in for n there. So our first term will always be, for any quadratic sequence, a plus b plus c. So that's a useful thing to know, and part of the explanation for why the other rules that we were using work out nicely. So our second term, let's call it u2. What does that work out as algebraically? So we substitute 2 into the formula and we get 2 squared 4 times a. Yeah? So 4a. We substitute it into the n term part of the function and we get 2 times b. In other words, 2b. Plus our constant c. And let's do our u3 as well, our third term. So we get 3 squared, that's 9a, plus 3b, plus our constant c. And you can see the sort of pattern as that builds up. So we could easily do u4, u5, u6, and so on. But that's enough to give us some algebraic rules. So let's do the first difference. Let's find the difference between these terms. So if we just draw a line like that, and we're going to write underneath the first difference. So let's just go ahead. No, let's write down first difference. Okay. Which we were calling D1 for short, but let's just write first difference here to start with. So our first difference is basically when we subtract u1, sorry, from u2. So what are we going to get when we subtract 4a plus 2b plus c? We're going to subtract a plus b from 4a plus 2b plus c. Well, 4a subtract a is simply going to give us 3a. So nice and straightforward. 2b subtract b will give us b. And c subtract c will give us 0, so we don't need to write that down. Now, we're expecting that u3 subtract u2 is going to give us a different expression, but let's see how it works out. Okay, because we don't get a constant in the first difference. So 9a subtract 4a will give us 5a this time. 3b subtract 2b will give us just b. So exactly the same as here. And again, c subtract c will cancel one another out. So you can see now why we're going to get between this term, let's write it here, u0, this term and the 0 term, which we found was so useful for calculating, there we go, for figuring out the what the term-to-term rule is. So the 0 term, we did that, if you remember, by taking the common difference away. But so what's it going to be? Well, the second difference down here is going to be 5a plus b subtract 3a plus b. Okay, 5a subtract 3a is going to give us 2a, and b subtract b again is going to cancel out. So if we subtract 2a from 3a plus b, we can see that here in our difference between the first term and the second term, we're going to just get a plus b. Let's write it just this side of this line. A plus b. So if that's the first difference, a plus b, that's one of the really useful things that we wrote down in our calculations. We use the idea that a plus b, in other words, the difference between the first term and the zero term, a plus b, has to equal, well, whatever it equals. Okay? So, if we subtract a plus b from a plus b plus c, well, what do we get? C. So the zero term equals c. So a plus b gives us this term here. Let's just highlight it. When we work out the pattern, and our c term comes from this term here. Alright, and finally we've got our second difference, which equals 2a, which is here. And you can check this again, simply working these things out. It's a lot of fun and reassures you that the formulae that you use in any of these problems is actually not, it hasn't sort of magically come out of the air, it has actually been derived, it does work, and it's a really good idea if you can understand that and also derive it yourself. Okay, so 3a plus b, subtract a plus b is going to give us 2a, b's cancel again. So again we've got this constant in our second difference. So that's how it works. That's why the second differences of quadratic sequences are constant and equal to 2 times a. It's also what gives us this a plus b term, which helps us with our method, and here is our u-intercept, our c constant. Okay.